general relativity step by step. Last time I was making the observation that we should be choosing, or certainly for dealing with relativity, we should be choosing time units and length units such that the speed of light is equal to 1. So what implications does that have? Well, that means that when I draw my, I'm in red. When I draw my axes here, this is my coordinate system here. Oops, let's just do that again. I'm going to pinch in a bit. When I draw my, try again, just a minute. There we go. When I draw my coordinates t and x for time and space, then light travels at 45-degree lines. Any actual object travels slower than the speed of light. I don't want this to be I don't want this course to get sidetracked by special relativity. I'm going to assume that special relativity is something that's kind of understood, and I just want to remind you about the various concepts as we go. So we've got our light paths here, and the world line of any object is constrained to be within that path of light. You cannot go along here because that is travelling faster than light. No object can travel along that path there, but you are free to move along here, and of course at any point, I've got a point here, I've got another light set of paths, and so my world lines are constrained to be within their light cones. The reason I say light cones is that here I've suppressed the y and z axis, so it's quite often the case that you see quite sharp diagrams like that have introduced. We've got time going up in that direction, we've got x there, and we've got another spatial dimension here, y. So it looks like a cone, of course, and sometimes you miss that line out and sometimes you join it up. So you've got a notion of you've got a sort of three-dimensional object that is representing two-dimensional or two physical dimensions of space and one of time in this light cone here. So there we go. The observation I want to make here is that if I go back to my coordinate system made out of girders, then we seem to have a bit of a problem here, because of course my light cone and his light cone should be the same in some sense, and they don't look like they're the same if we just transform the velocities as we expect them to transform. So I'm going to introduce in the next screencast, I'm going to introduce the Lorentz transformations. And we'll see that these Lorentz transformations maintain the constancy of the speed of light and maintain local physics, but they require a certain amount of mathematical sophistication, which I'll introduce in the next one. Okay, stop.